In the last lecture we had seen that in a single mode fiber, in addition to material dispersion, we have what is known as waveguide dispersion, and these material dispersion and waveguide dispersion, they occur due to finite line width of the source because of different wavelength components that are present in the light coming out of the source. So, these two dispersions are also known as chromatic dispersions. Waveguide dispersion occurs because the mode propagation constant of LP01 mode of a single mode fiber depends upon the wavelength. So, in the last lecture we had worked out the expression for the waveguide dispersion by first calculating the group velocity of the mode. In the process of working out the waveguide dispersion, we had assumed that N1 and N2, that is the refractive indices of the core and the cladding, do not depend upon the wavelength. So, we had not considered the wavelength dependence of the refractive index of the material of the fiber in order to explicitly bring out the effect of waveguide dispersion. So, in this lecture we will see on what parameters of the fiber the waveguide dispersion depends on and how can we tailor the waveguide dispersion. So, the expression that we worked out for waveguide dispersion coefficient is given by dW is equal to minus delta N2 C lambda naught times V d2 BV over dV square. We know how B depends on V. So, if we work out this V times d2 BV over dV square, then we can find out waveguide dispersion. So, apart from this, which depends on the value of V only, in this expression we also have the cladding refractive index and the value of delta, that is the relative index difference between the core and the cladding. When we plot this dispersion coefficient as a function of wavelength, what we find that waveguide dispersion is always negative for silica glass fiber for these particular values of different parameters corresponding to a step index fiber. And if I look at material dispersion for fused silica glass, it goes like this. So, I see that it is negative for wavelengths shorter than 1.27 micrometer and it is positive for wavelengths longer than 1.27 micrometer. So, the total dispersion, which is the summation of the material dispersion and waveguide dispersion, is around 0, is 0 around a wavelength 1.31 micrometer, and below this wavelength the total dispersion is negative and above this wavelength the total dispersion is positive. What is the meaning of negative and positive dispersion? Let us understand that. Does it mean that negative dispersion compresses the pulses and positive dispersion expand the pulses, broaden the pulses? No, both the dispersions will broaden the pulses. Okay. If the input pulse is unchirped, if the input pulse is unchirped, then both the dispersions, negative dispersion and positive dispersion, will broaden the pulses. Let us understand the meaning of negative and positive dispersion. So, to understand this, first of all I should understand why the broadening happens. The broadening happens because the spectral components have different velocities. The mode which is excited at different spectral components has different velocities. Now, when these components have different velocities, then I can have two possibilities. One possibility is the shorter wavelength components travel faster than longer wavelength component, and another possibility is longer wavelength components travel faster than shorter wavelength components. Okay. So, what happens is that if I plot, to understand this, if I plot group velocity as a function of wavelength for a typical silica glass fiber, then it goes like this, step index fiber. Now, let me pick up a point somewhere here, okay, which is less than 1.3 micrometer wavelength. Then I know at this wavelength, I have just seen that at this wavelength the dispersion is negative. If I take my source at this wavelength, and then this is the center wavelength, and then I see the components in the vicinity, wavelength components in the vicinity of the center wavelength, then I find that the shorter wavelength components have smaller velocity, while longer wavelength components has larger velocity. So, shorter wavelength components travel slower here, and longer wavelength components they travel faster. So, if I launch a pulse at this center wavelength, and this is unchirped pulse, then the fiber at this wavelength gives you negative dispersion and pulse broadens, because the shorter wavelength components travel slower than longer wavelength components. Okay. So, the pulse is broadened, but what I also see in this broadened pulse, that the frequency content in the leading and trailing edge is different. But I see that in the leading edge the frequency is lower, while in the trailing edge the frequency is high. So, the pulse not only gets broadened, but also gets chirped, and chirping is like this. While if I take my laser source somewhere here, then I know at this wavelength the dispersion is positive, and if I look at the group velocity of the shorter and longer wavelength components in the vicinity of this around the center wavelength, then here the shorter wavelength components travel faster and the longer wavelength components travel slower. So, now if I launch a pulse around this center wavelength, again the unchirped pulse, then it will experience positive dispersion and it will give you a broadened pulse like this, which is chirped in the opposite direction. Okay. So, here what I get, the leading edge has higher frequency component, while the trailing edge has lower frequency components. So, because of this I have negative or positive dispersion, but both the dispersions will broaden the pulse if the input pulse is unchirped. So, this is the intensity of the pulse. So, if I launch a pulse at z is equal to 0 at the input end of the fiber, unchirped pulse, and I see how it evolves along the length of the fiber, then I see that it will get broadened. If I capture this pulse at z is equal to 0 at the input end and z is equal to L, that is the output end, then it would look like this. So, the pulse clearly gets broadened, but the total energy in the pulse will always remain the constant if I assume there is no attenuation. In the absence of attenuation, the total energy in the pulse remains the constant. So, when the pulse broadened, its amplitude goes down, okay, or its peak intensity goes down, so as to have the total energy conserved. Now, this waveguide dispersion depends upon various waveguide parameters, because it is purely due to the wavelength dependence of propagation constant of the mode. Now, if my fiber is such that beta depends upon lambda, and if I change the fiber parameter, this dependence of beta on lambda can change, or dependence of n effective on lambda gets changed, then the dispersion will be different. In order to show this, I have taken several examples. So, one of the examples is that I take a fiber with delta is equal to 0.5% and A is equal to 3 micrometer. And now, if I calculate the effective index of the mode at different wavelengths and plot it, then effective index varies something like this. If I change the parameters of the fiber, make delta from 0.5% to 0.75% and bring down A from 3 to 2.5 in order to keep V value almost at the same level, to keep the fiber always single moded. If I am increasing delta, I will have to bring down the value of A. So, now again if I plot n effective as a function of lambda naught, then it goes like this. I see that the slope of this is different from the slope of this, and hence d2bv over dv square for both these curves would be different, and this will lead to change in waveguide dispersion. So, it will change the waveguide dispersion if you change the fiber parameters. In order to demonstrate this, I take numerous examples now. This is from the software LightSim. So, where I can change the relative index difference delta, I can change the core diameter and then see what happens to dispersion. So, this is when delta is equal to 0.0015, that is 0.15%, and core diameter is 10 micrometer. Then I see that at around 1560 nanometer wavelength, my waveguide dispersion is minus 4.28 picoseconds per kilometer nanometer, and the total dispersion is about 18.22 picoseconds per kilometer nanometer. Graphically, if I look at it, the waveguide dispersion is shown by this blue line, and the total dispersion is shown by this red line. So, the zero dispersion wavelength for the total dispersion is around 1.3045. If I change the fiber parameters, if I increase delta to 0.2% from 0.15% to 0.2% and core diameter I change from 10 to 9 micrometer, then what I see that the waveguide dispersion increases to minus 5.17 and the total dispersion becomes 17.33, and the total dispersion wavelength changes to 1.31 micrometer. So, when I change delta and A, I change the waveguide dispersion. I further increase delta, so it is now 0.3% and core radius is 8, then this is the waveguide dispersion, this is the total dispersion. If I further change it, then I increase the waveguide dispersion to about minus 8 picoseconds per kilometer nanometer. If I further increase, so I see that if I increase the value of delta, then my waveguide dispersion is changing quite a lot. Okay. If I am increasing delta, then the magnitude of waveguide dispersion is increasing. Okay. And the total dispersion is decreasing. Here at delta is equal to 0.7% and core diameter 5 micrometer, zero dispersion wavelength could be moved to 1.426 micrometer, which was earlier 1.3 micrometer or 1.31 micrometer. So, I can drastically change the waveguide dispersion if I change the fiber parameters. What I also notice in all these curves is that for a given fiber, waveguide dispersion is larger, the magnitude of waveguide dispersion is larger at longer wavelengths as compared to at shorter wavelengths. Why it is so? It is understandable because at longer wavelength the field spreads more into the cladding. At shorter wavelengths, field is more and more confined into the core. So, at shorter wavelengths, the mode does not see much effect of the cladding. So, the dispersion is small because it does not see the composite structure so strongly. But when you increase the wavelength, then your field spreads into cladding also. Okay, so the fraction of power that goes into cladding increases. So, the fiber mode sees more and more the composite structure and the wave guidance is affected more and more. So, with wavelength. So, that is why at longer wavelengths I see much stronger effect as compared to at shorter wavelengths. Now, can I tune my fiber parameters in order to get a desired value of waveguide dispersion? Is it possible? So, for that, if I look at this expression of waveguide dispersion, then it goes as dW is equal to minus delta N2 divided by C lambda naught times V d2 bV over dV square. Now, for a given value of V, this is fixed. Okay. If I want to obtain waveguide dispersion, certain value of waveguide dispersion at a given value of lambda naught, then, and I always use silica glass fiber, when I use silica glass fiber, then at a given wavelength this N2 and lambda naught, they are now fixed. N2 is fixed at a given lambda naught. Then what I can do now, if I change delta for a given value of V, then I can obtain a desired value of dW. So, if I fix dW, then I change the value of V and change the value of delta, then an appropriate combination of V and delta can give me a desired value of dW. So, I can understand it with the help of an example. If I want to target my dW as 22 picoseconds per kilometer nanometer at lambda naught is equal to 1560 nanometer wavelength, then N2 at this wavelength is around 1.4439. This is the refractive index of silica glass at 1560 nanometer wavelength. So, this is now fixed. N2 divided by C lambda naught is fixed as soon as I fix this wavelength 1560 nanometer. So, it is 1.4439 divided by 3 into 10 to the power 8 meter per second times 1560 into 10 to the power minus 9 meters. This is the wavelength. So, if I work this out, then this comes out this comes out to be 0.0031 second over meter square. So, this is fixed. Now, I vary the value of V, let us say from 1.5 to 2.5, and I get this V times d2bV over dV square, for example from Marquis formula, which I have shown in the previous lecture, that it gives you much accurate value of V times d2bV over dV square, okay, for any given value of V lying between 1.5 and 2.5. So, I get this from Marquis formula and then vary delta and then calculate delta in order to obtain dW is equal to 22 picoseconds per kilometer nanometer. So, I do that and I plot it as a function of V. So, if I vary V, so what values of delta will give me waveguide dispersion of minus 22 picoseconds per kilometer nanometer at lambda naught is equal to 1560 nanometer. So, this is how it varies, that delta varies with V like this in order to obtain this value. Okay. Correspondingly because I am changing delta for a given V, then A has to change to keep the V constant. Correspondingly, the core radius varies like this. So, you are increasing the value of delta, then correspondingly the core radius should decrease in order to keep this V constant. So, what I see that if I vary delta, then to keep the delta less than 1%, I would like to keep delta less than 1%. Yeah, I would not like to have very large value of delta, because if I increase delta, then attenuation in the fiber increases. Okay. So, if I typically keep the value of delta is smaller than 1%, then these are the combinations of delta and A that will give me the waveguide dispersion of minus 22 picoseconds per kilometer nanometer. So, I see the value of A would be around 2 micrometer. So, in this way I can obtain any desired value of waveguide dispersion as I want to certain extent, not any desired value, because if I want to have much larger value of waveguide dispersion, then perhaps I will have to have very large value of delta and correspondingly very small value of A, which is not desirable, because very high value of delta will give you very large attenuation and very low value of delta will very low value of A will make problems, will create problems in coupling light from source, laser source into the fiber. So, we will have to be practical. Let me work out an example. I consider a step index optical fiber with core refractive index 1.45, cladding refractive index 1.444 and core radius 4.2 micrometer, and I want to calculate broadening due to waveguide dispersion, okay, at lambda naught is equal to 1.55 micrometer, okay, and using Marquis formula. So, I want to calculate waveguide dispersion coefficient. Okay. So, solution is, well, what I need to do first, I need to find out this V times d2Vv over dV square. So, I first need to find out what is the value of V at lambda naught is equal to 1.55 micrometer. So, V is given by this. So, if I calculate V, then it comes out to be 2.2435, and Marquis formula for V times d2Vv over dV square is this. So, if I put this value of V, then the expression the value of this comes out to be 0.2714. Delta for this is I need delta also. So, delta if I work out for these values of n1 and n2, then it comes out to be 0.0041. Now, I have everything in place. Okay, I need to just plug in these values into this formula and get the waveguide dispersion coefficient. So, dW, which is given by minus delta n2 over c lambda naught times V2 d2 EV over dV square comes out to be minus 3.48 into 10 to the power minus 6 seconds per meter square, and I can convert it into picoseconds per kilometer nanometer, and it comes out to be minus 3.48 picoseconds per kilometer nanometer. So, till now we had considered step index optical fiber and waveguide dispersion in step index optical fiber. We can also work out this waveguide dispersion in graded index optical fiber. So, in graded index optical, the only thing is that you need to calculate the effective index as a function of wavelength. Okay. So, this we have done using the software LightSim, where there is an option of calculating dispersion for graded index optical fiber. So, I just want to tell you how the profile, refractive index profile of the fiber changes the waveguide dispersion. So, here I have power law profile. So, this is triangular profile which corresponds to Q is equal to 1. I have taken delta is equal to 1% and core diameter 4, and this is how the waveguide dispersion and total dispersion vary. So, at 1550 nanometer wavelength, if I pick out the values of waveguide and total dispersion, then the waveguide dispersion is minus 23 picoseconds per kilometer nanometer, and total dispersion is about minus 2 picoseconds per kilometer nanometer, very small. And the zero dispersion wavelength shifts to about 1565 nanometer. If instead of taking this triangular profile, I take parabolic profile, I am sorry, it has to be parabolic profile, it is not triangular profile. So, it has to be parabolic profile. So, in a parabolic profile, if I again take the value of delta as 1% and the core diameter I have now made 3. So, now the total dispersion, waveguide dispersion, they vary like this, and at 1550 nanometer wavelength, waveguide dispersion is minus 24 picoseconds per kilometer nanometer, and total dispersion is about minus 3 picoseconds per kilometer nanometer. So, by changing the profile, you can change the waveguide and total dispersion. This is cubic profile, which corresponds to Q is equal to 3. Delta here is 0.6%, while the core radius is 2 micrometer, and lambda naught at lambda naught is equal to 1550 nanometer. The waveguide dispersion is minus 21.68 picoseconds per kilometer nanometer, and total dispersion is very close to 0. It is 0 picoseconds per kilometer nanometer. So, zero dispersion wavelength here I have got 1550 nanometer. So, in this way I can even shift my zero dispersion wavelength, I can tune my zero dispersion wavelength at a desired value if I change the fiber profile. So, I have seen step index fiber, I have seen graded index fibers. I can also have multi-layer fibers where core is not made up of only one layer, but I have 2 layers in the core, one high index layer, then surrounding it is a small index layer, and then you have a cladding. So, I can have a multi-layer, and with the help of multi-layer I just want to show you that you can drastically change the waveguide dispersion. Just look at the values of waveguide dispersion here, they are less than minus 75 picoseconds per kilometer nanometer. So, the magnitude is larger than 75 picoseconds per kilometer nanometer. So, you can enhance the waveguide dispersion quite a lot. Okay. So, with the help of multi-layer structures you can considerably tweak with the waveguide dispersion. Okay. So, in this lecture what we had seen that waveguide dispersion depends upon fiber parameters, profile of the fiber. So, by changing the fiber parameters and refractive index profile of the fiber, we can tune waveguide dispersion to whatever value we want to certain extent. Thank you.